Alright guys, another quadratic optimization problem. Now remember, optimization usually means that we're referring to a maximum or a minimum, because we're either trying to maximize the profits or maximize an area or something, or trying to minimize something so we get the most value out of it. Okay, so here we've got 500 meters of fencing available to make 4 rectangular pins of identical shape. So if that's the case, we want to find the dimensions that maximize the area if the plan looks like this. Okay, so I'm going to mark each of these. I'm going to have x's for my widths there, or lengths. It doesn't really matter which is which. And then I've got y's here for the other one, right? Because these are rectangles, so these have to be the same. Those don't necessarily have to be the same. But I notice that when I add all those together, when I add all the pieces of fence, I've got 6x plus 6y equals 500. Okay, now I'm going to go ahead and simplify that just a little bit by dividing everything by 6, because then I'm going to have x plus y equals 500 over 6, which is the same thing as 250 over 3. All right, now since I'm looking for area of each pin, this pin is an area of x times y, right? Length times width, and so that will give me the area. Now again, I don't want 2 variables in addition to the area, which is the thing I'm maximizing or optimizing. And so let's go ahead in this equation. We're going to solve for 1 variable. I kind of like to keep my x's. If 1 variable is easier to solve for than the other, then definitely do that. In this case, it doesn't really matter. So let's go ahead and just subtract x from both sides. And I've got y equals 250 over 3 times x. We'll go ahead, put that in. So we'll have x times, that's definitely a minus there, sorry about that, times 250 over 3 minus x, so that's our y, right? That's what we had right down here, equals 500. Now, again, the maximum is where I get the vertex, right? So there's a couple of ways to do this. One, since is, well, sorry, why did I say the area is 500? That is a mess. Equals the area. Yeah, you thought you caught me. No, I caught it too. So there we go. Let's go ahead and distribute the x to both of these. So then we got 250 over 3x minus x squared. Now technically you don't have to do that. You can just find the intercepts, right? So if I found the intercepts, my intercepts would be 0 and obviously 250 over 3, right? And so I could actually find the vertex by finding the number that's halfway in between those. And so if my graph looks like this, going from 0 to 250 over 3, then the number right in the middle of those would be 250 over 6, right? So add those together, divide by 2, I'd get 250 over 6. That's one way of doing it, or 125 over 3. The other way, of course, is to do negative b over 2a. So b is the number in front of the x, so that's 250 over 3, and this is negative b over 2 times a. A is negative 1, so that would simplify then to negative 250 over 3 divided by negative 2. And so when you do that, you'll get the same thing that I got up there, which would be 250 over 6. So either way, we found the x value of the vertex. Now once we've got the x value of the vertex, we can just plug that in to get the y value. So I found out that the x value, now this is the x value of the vertex, so the x value of the vertex is 250 over 6, which is 125 over 3. So that's what we're going to do. We're just going to plug it back into this one right here. So x, this one right here. So x, which was 125 over 3, plus y equals 250 over 3. And then when you subtract that over, you get, surprise, surprise, 125 over 3. The dimensions have to be the same. It should kind of make sense. As long as you've got to make fence everywhere, then obviously a square is going to be your best option. It's going to maximize the area. And so there you go, 125 over 3 times 125 over 3. Cheers.